Now you can do this more elaborate, there are other artifacts. Let me show you one. So you're going to see a nightmares picture now. For some of you this will induce nightmares, okay? So please tell your children to not watch. What you see now. Okay? So what do you see in here? What do you see? How many people see Carrie? And how many people see Bush? Okay. So now, let's look at this. How many people see Carrie? Nobody, right? Okay, this is Bush. So before I showed you more pictures with roughly 50% Carrie, 50% Bush. Now you're just looking at pure Bush. And now I'm going to show you the same picture again I showed you before. So now most of you should just see Carrie. So you can do this in a lab and it works. So here you have a face-specific artifact. What happens that just like for colors, you also have for faces, this is a new discovery. For faces, you also have an opponency representation in your head. And if you look at an ambiguous picture, like one that consists half Bush, half Carrie, first you see, depending on circumstances, if I show this you 100 times, roughly 50% times you'll say it's Carrie, 50% time you'll say it's Bush. If you have to make a very quick decision. Now for 1 minute I make you look at just at one picture of only Bush. Your neurons fatigue after a while, they adapt. And so now if you see the previous picture, you're much more likely to see Carrie. So this is called the face-specific artifact. So now just like before with the color artifact, you could also do, but using a more sophisticated technique that I'm not going to describe, essentially you train people to recognize 4 different faces of these gentlemen, none of which I think you want to invite over for dinner. They're actually all they're all actually nice scientists, but they all look like escaped convicts here. Because sort of people, they removed facial hair. And anyways, they're so-called anti-faces, and you can do a sophisticated technique that essentially hides these faces from view. So you can use it, as I mentioned, we now in the lab have a number of techniques that very effectively can hide things for up to 1 or 2 minutes from view. So one of the most popular techniques is I show one image in one eye, and then I flash another image in the other eye, and you may not see that other image if I do things correctly for a minute or two, although it's presently in front of your eyes. You're looking at it, but you don't see it because it's perceptually suppressed by the input from the other eye. So using those techniques, I can show that in this case, it's very clear that for the face-specific after effect, if you do not see the inducing face, you don't get the face-specific after effect. In other words, for after effect for colors, I showed you whether or not you actually see the inducing color, doesn't matter, you still get the after effect. For faces, it's differently. Faces you actually consciously have to see in order to get the after effect. Now you can again say, well, that's very arcane, and why should I care about it? Well, it's interesting because it tells us that the neurons that are responsible for the conscious perception of faces, which we have some reasonable good idea about, because this you can locate in an fMRI scanner. A lady called Nancy Cambridge has done this at MIT. This seems to imply that those neurons have to be at the same stage, or after the stage where that the stage where the after effect happens has to be after the stage where the neural correlate for the conscious perception of the faces happens. So again, this helps you to pinpoint at the various stages on the brain where the neurons are that give rise to things like color or that give rise to conscious sensation of faces. And of course, those may not be the same neurons, and we know from already enough that to say that for things like colors, you have one set of neurons, and for things like faces, you have a different set of neurons. We know this. And partly we know this because you can have what's called prosopagnosia, where the patient will lose the ability to recognize a face. The patient can still say, yes, that's an eye, and that's a nose, and that's an ear, but he's unable to see consciously to put it together into conscious perception of a face. Why? Because the neurons that give rise to the conscious perception of face have been destroyed by the stroke. And so these sorts of experiments tell us a little bit about where they're located.